Hello and welcome to the Daily Space for today, Tuesday, September 10th, 2019. I'm your host for today, Dr. Pamela Gay, and I am here to put science in your brains. Today is hopefully going to be a better technology and life day than yesterday. Apologies for all of the chaos that we've been going through as I've been trying to figure out new ways to not apparently improve as intended our situation, but it turns out space is hard, and perhaps, well, recording a live stream is sometimes harder. I think we have things mostly under control, and we shall find out momentarily. I'm going to give this teleprompter thing one more go, and here's to hoping that it will actually work. So I'm going to bring up the slides. I'm going to try and bring up the slides. Come on, technology. There we go. And I'm going to reach forward and hopefully start the things. Today's news takes us far and wide. Nope, it totally didn't work. Okay. Pardon me for a moment while I reach and remove the teleprompter from its base. I just flung stuff all over the place. Okay, so here we go, trying again. Today's news takes us far and wide, but starts us off in a laboratory at Sandia National Labs, just outside of Albuquerque, New Mexico. Yes, that is the same Albuquerque where Bugs Bunny turned left. This experiment that we show in this picture here is the Z machine, and it's a pulsed energy experiment that allows temperatures of 4.1 million degrees Fahrenheit to be achieved. These are the same temperatures that are found deep in the heart of our sun. Now, our models on how the sun works are based on 4 basic observables. We can measure the sun's mass, its radius, its surface temperature, and its atmospheric composition. Based on those 4 different observables, which don't give us a whole lot of information, we have worked to put together models that take us from the very heart of the sun, predicting how much energy is being generated by what means, and carries us all the way out to the surface, making concrete predictions on how that energy is transported along the way. Now, while these factors put a lot of constraints on our theories, there just isn't enough data to allow us to test all of our assumptions. Some of the hardest to understand issues actually involve how various atoms absorb and emit light. Yeah, we don't always know how atoms absorb and emit light. It's one of those fundamentals that we really need to understand our sun. In astronomy, we refer to all atoms more complex than hydrogen and helium as metals. And the amount of these atoms in a star is referred to as the star's metallicity. These atoms act, to use a stretched analogy, like cooling rods in a nuclear reactor. They block the transmission of energy from one place to another and thus limit the rate of reactions. Now, atoms like iron don't block all of the light that's coming towards them. They aren't completely opaque, is another way to put that. If they were completely opaque, our sun wouldn't be able to have any nuclear reactions because iron is fairly common in the sun. The question has been, though, just how much energy do iron atoms and other complex atoms block? There goes my scroll. For decades, we've made assumptions based on what we know from lower temperature experiments. Sorry, let me start that sentence over. I know working from scripts isn't as free-flowing as just rambling at you. I'm just trying to get all the details correct, and I'm not actually reading the script, but I need my notes, and they keep trying to scroll away. I've now turned off the auto scroll feature. So the question has been just how much energy do these complex atoms like iron block? For decades, we've made assumptions based on what we know from lower energies, where we can work with them in laboratories, based on what we understand of quantum mechanics, and also based on what happens during nuclear explosions and other more controlled nuclear processes in power plants. Unfortunately, these estimates and our stellar models haven't meshed together to give us a really accurate understanding of the sun, and our models just haven't fully matched the reality that's shining over our heads during the day. This means either our stellar model has some flaws, or our understanding of atomic opacities, how much light those various atoms are able to absorb and re-emit, is flawed. So, using the Z machine at Sandia National Labs, scientists for the past 10 years have been systematically vaporizing heavy atoms like iron and actually measuring how much light iron is able to block and let transmit through. These measurements of this superheated plasma um, show us that it looks like the actual problem was in our understanding of atoms, and our understanding of the sun is pretty good. In a new paper in the journal Physics Review Letters, a team led by Tasuki Nagayama finds that iron is a much more limiting atom than we had previously understood. By adjusting how much light iron blocks in computer models so that it blocks more as they're seeing in the Z machine experiments, they're able to get models that are more closely matching our actual sun. While our overall models for how stars work seem to be turning out okay, this difference between prediction and reality for iron implies that our understanding of atoms is somewhat flawed. To try and model the atom's actions, physicists are turning to new models that explore the possibility that iron atoms can absorb more than one photon at a time. Well, that seems like no big deal. Sure, whatever, atoms can absorb two photons. The problem is that other atoms, like nickel and chrome, that they have also looked at in the Z machine, don't seem to absorb two photons. So we don't quite know what's going on, what makes iron weird. But at least now we have measurables. We understand chromium, we understand nickel, we've measured iron, not sure we understand it. It's a step forward. This is a complex problem, one that looks at the inner workings in atoms and expands out to dictate the behaviors of stars. This work, the result of 10 years' effort, is just a start. To quote project lead Nagayama, the science impact is enormous. This obligates us to continue examining the experiment's validity. Now, back when I was a graduate student, I heard a lot of people, especially those people who work in the field of cosmology, saying that we don't really need to expend a lot of effort and money on stars. Stars are a solved problem. But today's news makes it clear that even 2 decades later, stars and the structures they form are far from understood. One of the best ways we have to understand stars is to look out at clusters of stars. From looking at stellar nurseries that we call open clusters that exist in the disk of our Milky Way galaxy, to looking out at aged retirement homes in the outer regions of our Milky Way that we call globular clusters. All of these various clusters of stars are made up of, well, stars that all formed at the same time and with the same composition. That means they have the same amount of metals in their, well, everything. Now, our focus has often been on how individual stars that all have different masses evolve differently because of those masses. This is what makes clusters so useful. You look at them, all the stars are the same age, the same type. The only difference they have, star to star, is that mass. Now, it turns out you can also use these star systems and our understanding of stars to study how clusters dynamically change over time. In a paper coming out in the journal Nature, Nature Astronomy rather, a team led by Francesco Ferrara, uses our understanding of how stars look and how clusters dynamically evolve to, well, build a picture that shows us that just like people, not all clusters age the same way. Using the Hubble Space Telescope, they looked at a collection of 5 globular clusters in the Large Magellanic Cloud. This is a irregular galaxy that any of you down in the Southern Hemisphere or any of you who have visited the Southern Hemisphere during the right time of year are able to see. It was already known that young clusters of stars are all pretty compact, and that over time clusters will change shape. What's happening is the stars and clusters are actually interacting with each other gravitationally. And over time, the most massive stars will, through these interactions, settle down into the cores of clusters, while the smallest stars will get flung outwards and in some cases just get flung out of the cluster entirely. Exactly where a system is from the point of its formation, where it is small and compact, to the point when all of its massive stars have settled into the center, is referred to as its dynamical age. In this new research, Ferraro and his team lay out ways to define the dynamical age of a cluster by looking at one particular easy-to-see kind of star, and this is a blue straggler star. Now, blue stragglers are really weird stars. These are stars that essentially got a new lease on life by either forming out of the collision of 2 different stars that reignited as a bigger blue star, or as one star that cannibalized a whole bunch of material off of another star and reignited as a larger, higher mass blue star. No matter how they formed, blue stars are bright, massive, and easy to see because of their unique color. Now, what this team has been doing is looking at the positions of these blue stragglers throughout clusters and using their positions to judge the dynamical age of the cluster. A cluster in which all the blue stragglers have settled into the core is old, one in which they're still scattered throughout the system is still fairly young. Some systems, it turns out, more quickly shuffle their stars to their core, and others take more time to settle in. We don't fully understand why. It's going to take further observations to understand the factors that affect dynamical aging, whether it be the overall mass of the system, how compact it was when it formed, what was the velocity distribution of the stars as the system formed. For now, though, it's nice to know that just like people, the bodies of clusters don't always reflect their actual age. And, well, time may tick at a steady rate. We all age a little bit differently. In trying to understand our universe near and far, and here I forgot to show you the picture of the cluster. There, that's a cluster. This is one of the 5. This is the most beautiful of the 5 system. And the bright blue stars that you see in this are the blue stragglers that are being talked about. Okay, so in trying to understand our universe near and far, we often use what is closest at hand to understand. Thank you so much for that sub. You want to come here, Eddie? Come here. Since I've already paused, I'm just going to pause and give Eddie, well, his bits in exchange for your sub and your bits. Hi, do you like this? I'm going to be wearing Cheerios, aren't I? So we thank you for everything that you do with a little bit of fuzzy goodness. That's a good boy. Okay, so back to what is going to be a story about Titan. When we're trying to understand things far away, we often look at what is closest and, well, work on the assumption that what works here works far, far away. From using our sun as a model for understanding all stars, to using our Earth as a model to understand planets near, far in our solar system, and far beyond our solar system. Yeah, we just keep building on models perfected here to try and understand what's out there. Now, the thing is, as scientists, thank you so much for the sub. Now, Binary Blaze, you get to wait to get bits to the dog. So as scientists, we always have to keep an open mind. Thank you for the sub, Professor Melko. As scientists, we have to always keep an open mind and rely on creativity sometimes to help us understand what it is that we're seeing and not let our experiences bias us too much. This kind of creativity and this need to look beyond what is familiar was needed to understand the surface of Saturn's moon Titan. The Cassini spacecraft, during its decade or so of orbits, was able to collect data from radar and imaging instruments that showed us how methane and ethane have reshaped the surface of this world. These two, what we're used to thinking of as gases, form a complete weather system, and they actually carve out lakes and even river deltas in the icy surface of Titan. It's Titan's combination of low gravity and low temperature that allows this to happen. Methane and ethane essentially fill the exact same role on Titan that water does here on Earth, and exist on Titan at their triple points, allowing them to exist as vapor, as rain, snow, and to, of course, form that solid on the surface. Now, here on Earth, when we look at our landscape, we sometimes see these amazing lakes that form in limestone where rainwater has pooled, and over time, that pooling water has dissolved the limestone, creating special lakes that are called karstic lakes. And when we look at Titan, we see similar massive lakes. And here I'm talking about lakes the size of the Great Lakes here on Earth. And these massive lakes of methane and ethane seem to be formed the exact same way, where liquid has pooled and eroded away the surface to create these sharp-edged features. Now, while it was assumed that all lakes on Titan formed this way, that combination of radar and imaging data that Cassini was able to obtain had a few lakes that just didn't really fit that model. These lakes that are smaller, typically only tens of miles across, which compared to the Great Lakes is smaller, these smaller lakes have extremely steep, high edges, ridges around them that rise up from the surface. And when a lake has steep edges, this doesn't really explain how water was able to flow across the landscape and pool to dissolve the surface to form that lake. This meant that creativity was needed to figure out what exactly is going on. A new study published in Nature Geoscience suggests that a radically different process may be responsible for forming these lakes. What they suggest is that rather than being formed by liquid flowing in, these sharp-edged, rimmed lakes were actually formed explosively, much like how we see crater rims getting formed in explosions here on Earth. And here, when I'm talking about craters, I'm talking about like you explode something and it ends up with a crater rim. You slam in a rock from space, you get a crater rim, not volcanic craters. Now, I want to be clear. Nothing was ignited, nothing burned. This was not a chemical explosion. Rather, what they think happened was, in its past, Titan has gone through seasonal temperature variations. The methane that makes up its atmosphere and is amazing greenhouse gas. But methane is destroyed in ultraviolet light, such as our sun is constantly shining down on Titan. And it's believed that over time, the amount of methane in the atmosphere has ebbed and, well, increased. And during those times when there was less methane in Titan's atmosphere, there would have been less greenhouse effect, and the world's temperature would have dropped, allowing liquid nitrogen to pool in and under the surface. Now, when the planet rewarmed later, this liquid nitrogen would have changed phases, going from a liquid to a gas. And with this phase transition, it would have experienced a massive change in volume. And it's that massive change in volume of the liquid nitrogen becoming gaseous nitrogen that is the explosion we're talking about. So it looks like the change in temperature over time on Titan allowed these tens of miles across small lakes to form through an explosive nitrogen-driven process that isn't going on right now because of the thick methane atmosphere. Now, this kind of explosive lake formation isn't seen here on Earth. We don't have cases of nitrogen exploding and water quickly flowing in to form lakes, but that isn't to say this process isn't going on. Right now, with the buildup of greenhouse gases in our own atmosphere, just like there would have been buildup of methane, a greenhouse gas in Titan's atmosphere. With the buildup of greenhouse gases in our own atmosphere, we're seeing changes in temperatures of different regions on our Earth. Specifically, areas where there's permafrost are starting to no longer have permafrost. And in Siberia, they're actually seeing massive craters form as the permafrost melts and releases in essentially massive explosions, bursts of, methane gas. So here on Earth, it's the methane gas that is creating these craters that aren't yet filled with water, but could someday be similar crater lakes here on Earth. This is just one more case that shows that the same physical processes that happen on one world will happen on another. It's in the details that are driven by differences in temperature, differences in composition. It's in the details that we see variations. But, the science that works here works everywhere. And that pretty much rounds out today's Daily Space. Once again, I am your host, Dr. Pamela Gay, and I have been here to put science in your brain. In a moment, I will take your questions, and so I'm going to remind all of you to please at CosmoQuest X in the chat so I can find your questions. And while you're typing those in, I'm going to let you know that tomorrow, which is Wednesday, I will not be here. Instead, it's going to be Annie Wilson bringing you her weekly update on all the launches and landings and other spacecrafty goodness that are taking place. Thank you so much for the follow. I need to look at my phone to be able to see who that was. Thank you, Strecco93. We are a production of the Planetary Science Institute, and we are produced by Susie Murph. We are here thanks to the generous contributions of people like you. It's currently September, and we have a sub goal right over there. We are trying to get 50 subs by the end of the month, and we're already making good progress. Now, the only way we can meet that sub goal is with you. If you have never subbed before, it is your time to ask yourself, does this show help me out? Is this show worth as much as a really expensive latte at Starbucks? And if the answer is yes, please go ahead and sub. Now, if you don't want to sub here on Twitch, we get it. Because we're a 501c3, offer you many different ways to help us. And the best way you can actually help us is over on patreon.com, where you can become our patron. And as our patron, you will get special access to transcripts, notes, updates on what's going on, and a variety of other things. So please check us out over on patreon.com/CosmoQuestX. Now, if you ever miss one of these episodes live here on twitch.tv, don't be upset. It just means you get to miss out on the chat. This video in all of its chaos is going to get archived over on youtube.com. And for those of you who wish to avoid the chaos that is inherent in live broadcasting, check out our new podcast now available in iTunes, The Daily Space. Everything will be linked, hopefully by the end of the day, over on dailyspace.org and the RSS feed. If someone can type bang podcast, it will appear in the chat. Okay, I'm now going to look for your questions. And I'm sorry for the snuffling. I'm still fighting a horrible cold that I picked up. This is me scrolling. Hello, DPI. Hello, Paranor. Hello, R. Instro. Hello, Wayne Johnson. And thank you for the bits. Hello, Larry. Hello, DPI. I think I already said that. Hello, Planetary Pan. Hello, Revsmat. Thank you for whatever that is. I can't see that far. Thank you for following Vicrat3. Scrolling back to the top. Hello, Michael. Hello, Guido. Hello, Dave Killens. Scrolling. Hello, Veronica. Hello. Who else can I say hello to? Hello, Binary Ablaze. Hello, the Raven Lillian. Thank you, Mythtown, for the sub with Twitch Prime. Thank you so much. That's 8 months and a 7-month streak. Hello, Trekker Kev, and thank you for the bits. Okay, now I think I missed some questions because I was too busy saying hello to people. Looking. This is the confused while staring at my phone part of the show. So the cluster I showed isn't a Mega Centauri. It's actually, and let me pull up its picture again because it's beautiful. This cluster is one that is just labeled with a bunch of numbers and letters that is in the Large Magellanic Cloud. Oh, you shouldn't feel old, Larry. You should not. You're nowhere near as old as the universe. The universe is old. Thank you, Mythtown, for gifting subs. Thank you so much. Enjoy them, Binary Ablaze and Prof Melko. Get those emotes out, everyone. Hello, fellow hoodlum. Why are we sending a submarine to Io and Europa? Yeah, I'm okay with sending a submarine to Europa, but we need to learn how to sterilize them first. We're not quite there. Ganymede is icy as well, DPI 209. So here we're talking about the icy moons. Ganymede, Callisto, Io, and Europa are all the Galilean moons of Jupiter. Titan is a massive moon of Saturn. It's actually larger than the planet Mercury, which is why I try to be so careful to use the word world when describing it, because the word moon just really doesn't give it credit. Looking to see. I don't know if I'm missing questions. Okay, so Veronica is asking, can you share the blue stars picture again? There. There's a launch in 4 hours in Japan. Annie, let me know if you don't have it. Okay, Annie has the stream on the rockets. This is awesome. I will try to be in the chat. I need to run some errands today. Going to the post office is one of those unfortunate things in life that must happen. Let's see. Thank you, Walker MT, for the sub. I'm still looking for questions. I'm feeling blind. Okay, I think I got all the questions. If I didn't, please type them back into the chat and I'll go back and answer them. So my plan for today is I'm going to go record this episode as a podcast and push that out to all your favorite podcatcher feeds. And I'm going to hope that all of you take a moment to subscribe, even if you don't listen to us immediately. I am going to do a telecon because that's an unfortunate part of a scientist's life, run some errands, And then I'm going to be doing a bunch of web work. And if I get stuff that isn't CosmoQuest related done first, and I still have time left, I'm going to work on coding CosmoQuest. And depending on what I'm coding at any given moment, I may live stream some of it if Annie isn't live streaming the rockets. If Annie is live streaming the rockets, I'm just going to join you all in the audience. And we can enjoy a rocket lunch together. So, yeah, this has been the Daily Space. We are brought to you by you. We are here thanks to the generous contributions, the subs, the bits, the patronage on patreon.com/CosmoQuestX. Everything you do allows us to do what we do. And I'm so grateful that we are able to actually pay a living wage to Annie and to Susie, who does all of our production. So thank you for helping us make that possible. We are a production of the Planetary Science Institute, a 501c3 nonprofit dedicated to exploring our solar system and beyond. And I think that's it. We are here most Mondays through Fridays at 1 p.m. Eastern. That's 10 a.m. Pacific, 6 p.m. London time. And I believe Oh Bother is streaming. And we will, in a moment, give him a welcome raid. At least I hope he finds it to be a welcome raid. Oh man, I did it again. I forgot to open the window that allows me to start the credits that I can see from on this side of the room. Annie, if you can start the credits, I would be so amazingly thrilled. I'm sorry. So technological fail is the word of the day. I am working to change that. I'm not sure how. I'm just experimenting wildly in my basement, trying to get all the technology to work. I will figure this out. There are the credits. Okay. So wherever you are in the world, may your technology work far better than mine, because I wouldn't wish this on any of you. Wherever you are in the world. Have a fabulous morning, evening, or afternoon. And remember, if the weather allows, get outside and look up. I'll see y'all later. Bye-bye.